We are discussing memory management techniques. The basic principle involved is to separate out the logical address as generated by the CPU from the physical address where the program has been loaded and is being executed. This mapping is done by means of the memory management unit and is done at the execution time. The basic schematic is as given in this diagram. Here is the central processing unit. The logical address is generated from here. Here is the memory management unit, and here the process has been loaded. We have discussed already the partition management scheme. We call this a partition. This partition can move anywhere in the memory, and as it moves, the load informations of this partition is loaded into the memory management unit, and the address that is specified, the logical address that is specified, is mapped to the physical address in the memory accordingly. Now, one problem with the partitioned memory management scheme is this, that you will have to allocate contiguous memory locations. This partition has to be in a contiguous memory location, and due to this, the problem, an important problem arises, that is that fragmentation. Now, we shall today discuss a scheme where this contiguity of allocation need not be there. This scheme is called the paging scheme, and let's see that what is a paging scheme. First, let me define paging. Okay, I have taken a very small example, a very small virtual address, okay, the logical address of a process. It consists of only 32 bytes from here to here. Now, to address any location in these 32 bytes, that means within the address space of the virtual address space of the process, we need 5 bytes that have been shown in the green here, 0, 1, 2, 3, and 4. Now, these 5 bits, okay, generates an address starting from 00000 to 11111. Now, just look at these first 8 bytes here. If you look at the first 8 bytes and the addresses of the corresponding byte, you will see that the most two significant bits, third and fourth bit of the virtual address, which has been shown in the pink here, are 00 for all of them. The rest is this least 3 significant bits, that is lower 3 bits, 0, 1, and 2, will be 000 to 1, 1, and 1. Okay. For example, that this particular byte 0, 1, 2, 3 will have an address of say 0, 1, 1, and the most significant 2 bits will be 0 and 0. Okay. Now, this we call a page. For example, this we call the 08 page. Similarly, so for example, this byte here will have an address of say 0, 1, 1 with the two most significant bits 0 and 1. This is say page 1. Similarly, this is our page 0. Now, which essentially means what we have done is, what we can do is this, the virtual address can be divided into 2 components. The first 2 components here determines the page number. For example, if it is 00, then I am in 0th page. This is 01, I am in page 1. Then if it is 10, then I am in page 2. And if this is 11, then I am in page 3. Okay. And the complete address, that means, for example, if we have say 0, 1, then say 0, 1, 1, this 0, 1, 1 gives an offset say this is the offset of this particular byte, the third byte from the beginning of page 1. Okay. So the entire address space of 32 bytes we have divided into two components. We call these as a page number, the most two significant bits which designates it, and then offset from the beginning of the page, the lower three bits designated. Okay, and the entire address space, the virtual address space, is divided into 1, 2, 3, 4 pages, each page containing 8 bytes. Now, this is one way that we can do it. Another way that we can do it, that say for example, we say that the bit number 2, 3, 4, that will generate the page, and say bit number 0 and 1, that will generate the offset. In fact, in this case, what we have done is that we have 8 pages starting from 0 to 7, and each page will contain 4 bytes. According to our convenience, the convenience of the management, the entire address can be divided into two components. One we call a page number, another we call an offset from the beginning of the page, and simply we call an offset or a displacement. Sometimes we call this as a displacement also. Now, this is a situation we have shown very small address space. Now, what happens in the case of an actual or a real system? See here, we have taken a system in which the total virtual address consists of 32 bits, okay, which means it can go up to 4 gigabyte, okay, 4 GB. Now here I have shown a division of the entire virtual address in terms of page and displacement. Say we have taken 0 to 11 bits, the 12 bits as the displacement within the page, and from 12 to 31, 20 bits for the page number, which means that we can have 1 mega pages, each page consisting of 4 kilobytes. I have shown it here. You see that there are basically 4K bytes within a page, and page 0, page 1, page 2, page 3, that way 1 million such pages can be there. Now we can very easily see that if we simply shift this partition over to here, and the component is from 0 to 10, right, and from 11 to 31, that is the division we make, then the page offset, I mean the offset turns out to be 2K, I mean up to 2K, that means there can be 2K bytes here, and the total number of pages immediately turn out to be 2 meg, but the total addressability remains same, that it remains 4 GB. That way this partition of the two components can be shifted to make the page size and the number of pages that are involved in it. In practical situations, the page size of say 4K, 2K, 1K, even half a K are all acceptable, are all used, but mostly the system uses a page size of 4K. Now, this is therefore our paging scheme. The virtual address is divided into pages, and within the page we come to a particular byte by means of that offset. Now, how does it help us? Let's see how does it help us in our memory management technique. Here I have shown one, say, process here consisting of 4 pages, right? This is a virtual address space. Let me assume that it consists of 4 pages, P0, P1, P2, and P3. Here is the physical memory. That physical memory has been divided also into frames. We call them frames of same size as the page. That means if the page is of 4K, the physical memory frames are also of 4K, right? Now with this, what we do is this, say we arrange a mapping, right? Say simply what we do is this, say what we do is that let me assume that this is my process J0, and let's say it's a job J0 we call. As I said that for this discussion, the job, process, and program, I'll use the terms interchangeably. Say the processes P0 page of J0, say has been loaded into, I take this and load into the frame number 3. That means J0 P0 is loaded in the frame number 3, okay? And we create a table here where, say, since it's a 08 page, we say that this 08 page has been loaded into frame number 3. That informations we keep by putting 3 here. That means, say, this is corresponding to the page 0. This is corresponding to the page 1. This is corresponding to page 2. And this is corresponding to my page 3. This is a table that I create. I put page 0 of job 0 into frame 3 in the physical memory, and that information I kept in this table. We call this a page map table, PMT, or sometimes a page table, okay? Page map table, and sometimes in short we call it page table. Similarly, suppose that this page 1 I have loaded into, say, frame 6. That information I keep here. Then this page 2 is loaded into page 7, okay, sorry, frame 7. That information I keep here. And page 3 is loaded into, say, frame 10, and that information I keep here, right? Therefore, what we have done is that this frame is occupied, this frame is occupied, this frame is also occupied, and this frame, the physical memory, is occupied, right? The mapping of a particular page into equal size frame has been done by the operating systems, and as it does, okay, it keeps that information in a page map table, right? Now, say the process J0 is now executing. As it is executing, the CPU will start generating addresses. It will start generating addresses, the virtual addresses, which have the page number and the page offset. Now, since I have divided into page, okay, the address, the virtual address that is generated out of it will have the two components. We can think of in two components, that it has a page number and an offset within the page. Now, what we do is that which page number it is, that can the page number can immediately be consulted with that page map table. That means page number can be taken as an index to this page map table, and the corresponding frame number, say if it is page number 1, then the corresponding frame number 6 can be produced by the mapping function using this page map table. Then we can come to the, say, frame 6 and take that offset within this page, come to that offset over to here, and can access a particular location, right? Let me repeat once more. Here is the process virtual address. Whatever address the CPU generates consists of two components now, okay? It's a page number and then page offset, okay? Now, say a virtual address is generated in page number 1, okay, with an offset of say D. That page number that comes out of it, we can consult this page map table using this page number as an index. That means that this entry I consult, the operating system consults, the content of that page map table that of that particular location is 6. That is taken as the frame number. The displacement remains same. This displacement we take, and therefore we can come to this particular address to have ultimately the physical address. Okay, this is the way a particular process address space can be mapped into the physical memory, and you can see the contiguity of memories that has to be allocated to this process J0 need not be there. This has been divided in terms of the page, and the pages have been allocated frames, and these allocated frames need not be contiguous. That the frame 6 and 7 that is allocated to page 1 and page 2 is contiguous is just a coincidence, but naturally it need not be a rule. Okay, this way in the paging model, the page number to frame number mapping can be done. Okay, let's see what is the hardware for this page number page to frame mapping. Here you see that we have shown the central processing unit, right? The central processing unit is now generating the logical address. The logical address can be thought of as two components. Okay, it is considered as two components. One is the page number, another is the displacement within the page. That page number comes to the page map table. Okay, this P is used as an index. That means offset of that particular page map table corresponding page map table entry in the page map in the page table. The frame number is outputted. That frame number replaces the page number in the address. The displacement is directly comes as a displacement here. Therefore, that page displacement is now mapped into the frame displacement, and we get the physical address here, where this is F, the frame F, and this is the displacement D. Okay. The information, therefore, what is needed while the virtual address, as has been done, is divided and is loaded into different frames, is that corresponding the page map table has to be loaded with the corresponding frames. Okay. Now that is quite fine. Now let us see that if we have, say, another program, okay, having, say here, say this is the page P0, P1, and P2, and let the process number be J1. Okay. Now here there are many frames that is available. Say for example that P0 page of J1 is loaded here. That means this is say J1 P0. Correspondingly, the operating system immediately creates, okay, another page map table which has 3 entries. The job 1 page 0 has been loaded into the frame 8. Therefore, that 8 I enter here, right? This is the page map table of, page map table of J1. This is a page map table of J0, right? Therefore, you see that page 0 of job J1 has been loaded here this is now occupied, and this is the 08 page, this is the first page, and this is the second page of it. Say page 1 of job J1 has been loaded here. That means J1, page 1 is loaded here. Therefore, the frame number is 4. And say page 2 of job J1 is loaded into, say, the page number 1. Okay, that means it is loaded into page number 1, and we have, say, job 1, page 2 is here. Now, this is the page map table of J1, and this is the page map table of J0. When J1 is running, the operating systems will be consulting the page map table of J1, and when the process J0 will be running, the operating systems will be consulting the page map table corresponding to J0. Now, from here, it's very clear that what essentially we have done is that we have divided that entire physical memory into frames. The jobs or the processes address spaces has been divided into pages. The frame size is equal to the page size, and these pages are loaded into the memory in the different frames. As the frames are available, corresponding a page map table is created. Okay, for example, one page map table for one job. Here page map table PMT J0 for J0, PMT J1 for J1, and whenever a particular process is executing, the operating system makes it that the corresponding page map table is consulted to map the page number into the frame number. Displacement remain the same, and that way the corresponding frame and the displacement, taking the corresponding frame and the displacement, that particular location is accessed. Okay, that is, let me come to our paging hardware once more. Let us see here that central processing unit once more, that logical address generated, page map table for a particular process that is being executed by the CPU. The page number comes as an index to the page map table. The frame number is outputted. That frame number replaces the page number in that logical address to make it a physical address. The displacement remains the same, and with that physical address, we go to the frame number F and the displacement D to access a particular memory location, right? Now, let's see, that's quite fine. That a good mapping mechanism has been done, and the contiguity restriction that a particular process has to be allocated contiguous memory location, that has been removed. Okay, and we have the freedom of choosing any frame, okay, and putting a page of a particular memory, a particular process into that frame. Of course, one important thing that I should let me immediately address, so that I don't forget later on. See, though I have seen, so for example, this for this job J0, P3 is the last page. I have assumed here that as if that P3 has occupied that entire frame, but naturally, it will be such that P3 will not be occupying that entire frame. It will be, for example, if it's a 4K, that last page can be anything starting from, say, 1 by 2 4K, which means that if the P3 is not full, so for example, this is empty, in that case also, that frame 10 will not be full, and these portions will be empty. Therefore, a small fragmentation, a hole also here comes into the picture, and we call it an internal fragmentation. Therefore, per process, the last frame, the last page is not full, and therefore the last frame, last page where it has been mapped into the frame, that frame will not be full. Some memory locations in any case, in that case, will be wasted, and that is called as an internal fragmentation. Okay. Yeah. Now let's come back to this paging hardware once more. Now, one important thing now I'd like to point out, right? See, this is a page map table. This has to be consulted every time a memory need be accessed. Okay, and just remember one thing, and that's very important to remember, that this mapping is done at the execution time. That means whenever there is a mapping involved, that means whenever there is memory access involved, the logical address has to be mapped into a physical address, and that page map table has to be consulted. Okay, and where do we keep this page map table? Where the page map table has to be kept? Now, since essentially it is once more a memory, okay, which has to be consulted, this page map table is kept in the physical memory itself. Okay, this is our this page map table, somewhere in the physical memory, this page map table has to be kept. Okay, this is the PMT. Okay, this PMT has to be kept in the physical memory itself, which means immediately you see there is immediately a demand, okay, or it immediately affects the performance of the system, right? Say this logical address generated, first to consult the page map table and to get a corresponding frame, the physical memory has to be accessed. The frame number is extracted, and that frame number is put into this physical address, and then the physical memory is accessed once more. Okay, for example, therefore, for every access to a physical memory, for every memory reference, you see that I'll have to, the operating system has to, the total hardware has to access the physical memory twice, which means that in terms of the accesses, the speed of operation, the speed immediately turns out to be half. Okay, twice the time is needed to access any memory location of a particular process. Right. Therefore, this immediately naturally affects the performance, and we'll have to do something about it if we want to keep the performance acceptable or the performance good. This is one aspect of the problem that I say. Another aspect of the problem that I was saying is this, that there are many page map tables. If there are 10 jobs, there will be 10 page map tables. All the page map tables, in that case, will be in that memory, as has been shown, say, page map table for job J0, job J1, job J2, all will be in the physical memory distributed. Now, when the CPU or when the operating system switches from one process to the other, then how does the operating system finds out that particular page map table corresponding to the process which is now being brought to the running state and will be executing, which means the operating system has to keep a table where the starting addresses, okay, are kept in that table. That means pointers to the page map tables of the different processes have to be kept in a table, and that table has to be kept in the memory location. Whenever process switches a job, that means it takes out one job, one process from the running state and puts another process into the running state. The corresponding page map table have to be consulted. That which page map table has to be consulted in the memory, that is, that address is kept in that page map table, okay, pointer table, okay, page map table pointers, a table of pointers of page map tables, right? But you know, that immediately turns out to be a problem of immediate, so to say, that consulting that particular table. And what is done therefore is this: we keep what we call page table or page map table pointer. Okay, this is the hardware register. Output of that is now added with the page number of the logical address, okay, to come to the corresponding page map table entry. Let me repeat. So for example, if the entry of this page map table pointer is B, therefore in that case the output is B, that B is essentially here the base register, okay, base address. Sometimes it's called a base address also. Whenever the operating system switch to a particular process, it consults that page, the table of page map table pointers. The corresponding pointer value, that means base address of that page map table, okay, which is in the memory, is taken and is loaded into this page table pointer or page table base address register. Okay, this is a register. Now, so for example, I'm switching to this job where this is the page map table. Say this address is B. This B has been kept in some table, which is the table of page map pointers. When I switch over to the job corresponding to this page map table, this B is taken and is loaded into the page table pointer, and which means that starting from the B location, the page map table has started. Say this is the B address. The page number is taken from the logical address. It is added with the base register. This works as that offset or the displacement within that page map table. That means, for example, this is the P. I come to that P, take the frame from here, replace the page by this frame, and go to the physical address. Now, when I switch, the operating system switches from this particular job whose page map table is here to another job whose page map table is somewhere else, then its corresponding base value has to be loaded into this page table pointer, so that now this page table pointer points to the page map table, say this PMT of another process. Okay, its value may be say B1. Okay, right. Essentially, that means what? That means that operating system won't have to search for the page map tables. Okay, the page map tables addresses of the base of the page map tables are kept in that table. We have a register to make it fast. Whenever you switch job, the corresponding pointer to that page map table is put into that page map table pointer, and that register is utilized in this entire mapping hardware. Right. In this entire mapping hardware, this is in the memory. This is a register, this is a register, and this is a register, hardware register. But even now, to access any particular memory location of a particular page, you will have to, that means the hardware has to go to the memory twice, okay, so that for so the memory references are concerned, the speed of progress of the process immediately turns out to be half, right? For every memory reference, twice the memory has to be consulted to get the particular, to come to that particular location. Now, naturally, something now has to be done about if you want to speed up that entire process. Okay. Now, what is done is this. This is a diagram. Once more, it's a paging hardware that I have shown over here. You see, this is a virtual address generated, the page number and the displacement. Displacement straight comes over to here, and the page number, if we just forget about this portion, the red table, the page number comes directly to the page table as an offset, right? I have not shown the page table base register here, or page table pointer here. The frame number is taken, and the frame number should go into the frame, and I come to the physical address. Now, what we do is this, part of this page table, okay, we keep in a set of hardware registers we call translation look aside buffer, okay. Let me give the full name of translation look aside buffer, TLB. Sorry, translation TRAN, okay, look aside buffer. Translation look aside buffer, that is a TLB. Let's see what is a TLB. A TLB, as I've said, is a set of hardware register. Okay, it's essentially content addressable registers or content addressable memory, so to say, consisting of these registers. Each entry of this TLB, one entry is a page number and the other entry is a frame number. That means if the page 10 is loaded into the frame, say 205, right, then page 10 will be the first entry and 205, the frame where this page 10 of the process that is being executed has been loaded, it will be the other entry. Therefore, if we can come to this, for example, if we know that page 10 is here, then 205 will be outputted immediately and that frame number can come immediately to that to this component of the physical address. Now, you see that page table, as I've told you, that in the case of a real process, okay, the page table size can be as high as, for example, 1 million of entries, right? For example, if you say 4 GB, that address space can be, and if we say that 4K is a page size, then 1 million entries will be there in the page table. And such a huge hardware registers, okay, to map is not possible. That means, for example, instead of keeping the page table in the memory, if we could keep the page table in hardware registers, which are very fast, and if we have used this mapping, then the mapping would have been very fast. But as I said, since the page table size is too huge, if we have to keep so many of hardware registers, say 1 million of hardware registers just for the mapping, then it will be prohibitively costly, and therefore a page map table hardware cannot be implemented because it will not be cost effective. Then what can be done? What can be done is exactly that what we did in the case of cache memory. Okay, I hope that you remember in the case of cache memory, that part of that memory we have kept in very high speed registers, okay, high speed memories. Here also, in very high speed memory, we keep part of the page table. And in that case, since we only have kept the part of the page table in this very fast memory, which consists of registers, both the page number as well as the corresponding frame number into which the page has been loaded has to be kept, right? As I said, that if page 10 has been loaded into frame 205, both this information has to be kept, since the entire page table cannot be kept in these hardware registers. Now, what is done is that by the hardware does is that, and this is content addressable. That means, say here I have shown only 3 registers in the translation look aside buffer. All the 3, whenever a page comes, all the 3 locations are immediately checked simultaneously, okay, immediately checked simultaneously, and wherever there is a match, okay, if there is a match with the page table, the corresponding frame number is immediately outputted. For example, say, let me just to give an example, say this is 05, say 100, and say this one is 01, and say, for example, say 300. Say this information of this particular process has been kept here. That means page 5 is in frame 100, page 10 is in frame 205, and page 1 is in frame 300, okay, and the virtual address has been generated. See, the virtual has been generated is say 10. Now this information comes over to here. All the three buffers, okay, registers are simultaneously compared with 10. Here there is a match. 205 will be immediately outputted, right? The translation look aside buffer will indicate here that there is a hit, okay, like that our cache memory, it will indicate a hit. The multiplexer, this is a multiplexer. This multiplexer will allow this entry, okay, this input to come as an output. Therefore, this 205 will come over to here. The 10 will be replaced by 205 here, and we go to the 205 frame and a displacement D to come to the physical address. Okay. Now, since this is very fast, translation look aside buffer is very fast, you know the speed is immediately improved, right? Now, naturally, I mean, Joe I have shown in terms of only 3 registers. This is not so small, which is somewhat, it can be somewhat quite big, in the order of say some say for example 1000 of buffers can be there. Now, what happens if it is a miss? That means if you find the corresponding page is not here, right? Now, important thing, let me repeat once more, whether I've forgotten to mention is this. This is a content addressable memory. By that I mean, this is a content by which it is searched. Okay, P is the content by which it is searched. It is searched simultaneously in this TLB, that means compared simultaneously, and wherever there is a match, okay, that particular frame entry, that means the second entry, is outputted, right? And at the same time, it says that there is a hit. Now, but suppose instead of 10, say this is 15, the page number is 15, okay? Now, you see the 15 is not here. What happens then? Since 15 is not here, it will indicate a miss, and that miss information will come to the page table. This table is in the memory, okay? That page number in that case comes to the page table, which means the hardware now has to go to the memory to fetch the corresponding frame from here. That frame is now the input, one of the inputs of the multiplexer. Since it's a miss, you know, this input will be the miss, right? Either 1 or 0, say 0 for miss or 1 for hit. If it's a 0, then this input will be multiplexed into the frame number, and the corresponding frame F, okay, will be inputted here. And as is done, this frame will be put into the translation look aside buffer. That means this information, that 15 should come here, and the corresponding frame, so for example, say if it is 400, right? Say 400, this 15 400, that information will be put into the translation look aside buffer, right? If necessary, one of the entries will be removed, and this entry will be put over to here. Now, the frame number is available. The hardware can go to the corresponding frame, which will be now say 400 here, say 400 here, and the corresponding displacement is used to come to the displacement to fetch that, or to access that particular memory location, right? Now, the advantage is immediately, okay? If the hit ratio is very good, in just as was in the case of your say cache memory, if the hit ratio is good, in that case you can see our search is in the TLB followed by a memory access. But if it is a failure, that means it's a miss in the TLB, right? Then only the page table has to be accessed, right? Which means that in this case, depending upon whether there is a hit or a miss, okay, access time will depend. In the case of a miss, the access time is twice the memory access time, right? Twice the memory access time plus search time of the TLB, because the TLB will be searched first, then the page table will be searched, and then one goes to the memory. But if it's a hit, then it's a TLB search time followed by the memory access time, right? And since TLB is very fast, if the hit ratio is fast, then we gain immediately in terms of the speed, right? Just I have shown a simple measure for it. Say TLB search access time I have shown to be 25 nanoseconds, it is very fast. Main memory access time I have assumed to be 120 nanoseconds, and the hit ratio is 80%. Then effective access time will be 80% is a hit, therefore 0.80, we search TLB, we search a memory, okay? If you say miss, then the miss percentage is 20%, therefore it's 0.20, and then search TLB, then twice search the memory, one for the PMT and another for the access to particular location. And with this figure, the figure that we get of an effective access time is 169, which is, you can see, quite close to 120 nanosecond, and definitely is not 240 nanosecond, which otherwise we would have needed. Okay, therefore that's a good amount of speed up that we get if the hit ratio is quite high, right? Now let me stop here today. We will continue the rest of the discussion on this, that means the memory management, in the next class.